Now, recall that in the previous step, we have transformed, in order to prove the Picard-Lindelöf theorem, we have transformed a general initial value problem to the initial value problem at the origin. So now, instead of the initial condition be y of t0 equals y0, it's just y of 0 equals 0. So geometrically, it means that we translated the whole vector field so that the initial point becomes the origin. And algebraically, that there was a certain substitution. But in any case, if we want to prove the Picard-Lindelöf theorem, it is sufficient to prove it for the initial value problem at the origin. That's the main point here. Now, here comes the neatest trick in the whole theorem. And this is, I guess, what why Picard and Lindelöf, what they were genius about, is about inventing this trick. The trick is to translate the differential equation to the integral equation. Now, what is the integral equation? So this is our differential equation, right? So this is true. Y here is a function of t. So the left-hand side is the derivative of y with respect to t. And the right-hand side is f of t, and y is, again, is a function of t, so it goes like this. So then this is true for all values of t. If this is true for all values of t, it means that this function equals to this function, and therefore their integrals are also equal. So if we have an equality that holds for all values of t, we can integrate it. So we are going to integrate this from 0 to t. From 0 to t. But of course, when we are integrated from 0 to t, then t becomes the variable, the upper limit of integration, so we need to change this t to something else, for example, to s. Well, the right-hand side is just the integral of f as y over ts, but the left-hand side is the integral of the derivative, right? And the integral of the derivative, well, that's exactly the fundamental theorem of calculus. So this is the difference of the values of the function at t minus 0. So y of t minus y of 0. But y of 0, and now this condition becomes important. Since y of 0 is 0, it means that this just disappears because y of 0 equals 0. Right? So now the left part of the theorem, so by integrating our differential equation, we get this. So y of t equals this. So what we see is that if our original differential equation is true with this given initial condition, then this integral equation holds. Conversely, if the integral equation holds, is it true that our function satisfies this differential equation with this initial condition? Let's check. If we want to differentiate this with respect to t, so by taking d over dt of this whole thing. Now, this is true for all values of t. Therefore, we can differentiate it. Then the left-hand side becomes y prime of t. And the right-hand side, when we are differentiating the integral with respect to its upper limit, what we get is just the integrand. Then we get f of t, y of t. Which is exactly our differential equation. Correct. The initial value, y of 0, equals the integral from 0 to 0, f of s, y of s, ds. But the integral from 0 to 0, no matter what is here, is always 0. So checked. Right? So, in other words, if our integral equation holds, then so does our original differential equation and our initial condition. So, which means that our differential equation with the initial condition is just equivalent to this integral equation. Let me maybe give you a specific example so you can get a better feeling of this. My specific example is y prime equals t squared minus y. Now, of course, you can solve it. This is a linear differential equation. You can just solve it, or you can, I don't know, do it in Wolfram alpha. Yeah, I did it in Wolfram alpha. So the y of 0 equals 0. The solution is, let me find it in my notes. Yeah, I have it here. Is 2 square. Sorry. T square minus 2t plus 2 minus 2 e to the minus t. Now, this is a solution of this differential equation. Now, let me just show you that this is also a solution of this integral equation. Okay? So, integral equation. So, integral equation. In order to verify that it satisfies the integral equation, let me just substitute it to the integral equation. So, this is going to be the integral from 0 to t of what? This is the right-hand side of my differential equation. This is the right-hand side. Now, remember that t should be replaced with s. So, this is s squared minus y. And y is this whole thing. But again, this is y of s. This is y of t. So, I need to replace t with s. So, it's going to be s squared minus 2s plus 2 minus 2 e to the minus s ds. Now, if I integrate this, will I get back the original y? Let's check. This is going to be the integral from 0 to t. What do I have here? S squared minus s squared 0, minus minus plus 2s, minus 2 plus 2 e to the minus s ds. Now I can take the antiderivative. The antiderivative of 2s is s squared minus 2s minus 2 e to the minus s from 0 to t. Okay, excellent. When s equals t, I'm going to get t squared minus 2t minus 2 e to the minus t. And when s is 0, I have to subtract this, the same expression when s is 0. This is 0, this is 0, this is e to the 0 is 1. So minus negative 2 plus 2. And you can compare this and the original form. It's exactly the same thing. Plus 2, if I just move it here. So this is same as 1. So which means that this function that satisfies the original differential equation, it also satisfies the integral equation. Of course, the difference, I mean, if the differential equation is a linear differential equation, so we know how to solve it, we've learned it already. This integral equation, well, it seems a bit strange that we want to convert our differential equation that is familiar to the integral equation that is unfamiliar, because we don't really have any means to solve integral equations. But the reason for this is going to be clear later in step 3.